Welcome back to solution of ordinary differential equation using Euler method with Python. Here we also discuss two examples: freely falling body and projectile motion. So solution of ordinary differential equation using initial value problems. Here we find the solution of the ordinary differential equations. For example, let us take an ordinary differential equation like dy by dx equal to f of x y. So by finding the solution, we mean finding the value of y, value of this y at some x, that is y of x. What is the value of y of x? In initial value problems, we will be given an initial condition y of x naught is equal to y naught. There are different initial value problems for finding the solution of ordinary differential equations like Euler method, Runge-Kutta method, etc. So first we will discuss Euler method. Euler method is one of the simple initial value method for solving ordinary differential equations. The basic principle behind this method is integration. That is, we integrate this differential equation to obtain y. For some x equal to xn equal to x0 plus nh, we want to find y or y of x. So integrating this equation with respect to dx, we will obtain y like this: y1 equal to y of x0 plus h, this is equal to y0 plus integral of this into dx. In Euler method, we assume this f of xy in this interval x0, x1 as f of x0, y0. That is, this f of xy is assumed as a constant f of x0, y0 in this interval, so that this y1 becomes this y0 plus integral f of x0, y0 dx. Since this is a constant, this is taken outside, so this becomes y0 plus f of x0, y0 integral dx. Integrating with respect to dx and applying the limit x0, x1, we get x1 minus x0, that is h. So this becomes y0 plus h into f of x0, y0. Then the value at y at x equal to x0 plus h is obtained as y1. Similarly, for the second interval, the y2 is obtained like this: y2 is equal to y of x2 is equal to y of x1 plus h equal to y1 plus h into f of x1, y1. So generalizing, we get yn plus 1 equal to, that is y of xn plus 1, which is equal to yn plus h into f of xn, yn. So we will see some examples for this Euler method. First one, the freely falling body. Freely falling means the body is falling only in the presence of gravitational field. So all bodies, irrespective of their properties, will have the same acceleration, where this acceleration will be this g, the gravitational acceleration. So in the case of freely falling body, we solve a second order differential equation: d square y by dt square is equal to minus g, that is acceleration equal to minus g. So to solve this equation, we have to integrate twice, or we have to find the solution twice using the Euler method. So first we integrate this d square y by dt square and we get dy by dt. Using Euler method we get like this: dy by dt at t0 plus h is equal to the initial value of dy by dt, that is dy by dt at t0 minus g into h, or this into dt, that is minus g into h. So integrating once again, this equation provides y, dy by dt provides y, so that using Euler method this becomes y is equal to y at t0 plus h into dy by dt at t0 plus h. So in this case, in the case of freely falling body, we terminate this iteration, or this finding these y values, when the body touches the ground, or when y becomes 0. Now we will see the Python code for freely falling body. We initialize the time and velocity as zeros. Velocity as 0 means we drop the body with 0 velocity, and the g is taken as usual minus 9.8 meter per second square. This dt is taken as 0.1 second. Then the h is read where the h is the height of the fall. We initialize the empty list for storing the results. Print the titles while this height is greater than or equal to 0, means while the body is above the ground. We iterate this while loop. This a is g. Then using the Euler method, this velocity is calculated. V is equal to v plus a into dt. Then again integrating this velocity using Euler method, the y, or here the y is represented as h, the h is calculated, that is h is equal to h plus v into dt. Then the time is incremented. Then these calculated values are appended to their lists and they are printed as a table. The output is like this. As the time proceeds, the height decreases and reaches a value less than 0 and it exits the loop. The acceleration is constant and the velocity is increased. So this is the output for the freely falling body. Now we will see the second example for the Euler method, that is projectile motion. The projectile motion is a two-dimensional case. The acceleration of the projectile along x direction is 0, since there is no force along this x direction. The acceleration of the projectile along y direction is this minus g, that is the gravitational acceleration downward. By Euler method, the velocity is obtained by integrating these accelerations, but we know the velocity along the x direction will be a constant, since there is no acceleration along the x direction, that is ux equal to ux0 is equal to u cos theta, and the velocity along the y direction will be uy0 plus ay into dt. So again integrating using Euler method, we get the solutions x and y like this. x is equal to x0 plus ux into dt, and y is equal to y0 plus uy into dt. So this is the Python code for this projectile motion. The Pylab is imported for plotting this projectile trajectory, and this g is given as minus 9.8, and this y is read as the height from which the projectile is launched, and this velocity and the angle is inputted. This theta is converted into radians. Then the initial components of velocities ux and uy is calculated. Then the dt is set as 0.01, and the time and x is initialized as 0. Empty lists are created for storing the data. Then a while loop is started, and this while loop proceeds until the projectile touches the ground, that is up to y greater than or equal to 0. The values are appended to their lists: t data, x data, y data, and v data. And this y component of the velocity is found using the Euler method. Then the y and x is again found using the Euler method, where we know this Vx is a constant which is already calculated here, and the instantaneous value of the velocity will be square root of Vx square plus Vy square, that is hypotenuse of Vx Vy, and the time is incremented. Now these values are printed as a table. Now this is the plotting, this is the for plotting. The title is given as projectile motion, x is labeled as horizontal distance, and y-axis is labeled height, and this x data versus y data is plotted. So the result is like this. The printed table is like this. We inputted the height as 10, this height as 10, and the initial velocity as 20 meter per second, and angle of projection as 30 degree. Then these are the printed values. So this is the output plot. This is the trajectory of the projectile. From the height 10, it projects like this. Here it reaches the maximum height, and it falls down like this and reaches the ground.